Okay, great. So let's suppose you have a PyTorch model, right? So what you need to do is you need to convert, or need to reach a interchangeable format, right? And for TensorRT conversion, that format is the Onyx, right? So once you have a PyTorch model, you convert that to Onyx, and then using the Onyx import, or uh, the different Onyx model you have created, you can convert that the Onyx model directly to the TensorRT model. And the TensorRT has basically usually two extensions. One is .plan and the other is .engine, right? Pranav will share the other recordings, like we'll download the recordings for all the 5-day sessions, and then upload on a drive and then share with you, because on SharePoint we need to give access on email to email basis. Okay. So for the conversion, what you can do is there are two routes. Either you can basically there is this plugin or API which is TRT exec, right? That command you can use for conversion, or in some cases like 95% of the models, they are compatible with the TRT exec command, right? But sometimes we have observed that certain models they do not like convert well using that command. So hence the reason being, some layers might not be compatible, or you can say we do not support that layer in terms of TensorRT conversion. So for that you need to manually write a converter, and for that you can either use your C++ API or Python API for the same, to write the converter.py file or converter.cpp based on your comfort level, and that the conversion can also be done uh, depending on whatever model you are using. Now, inferencing with TensorRT, again, what we are going to do is you'll have basically you'll convert your trained neural network into a more optimized version. So here that version is TensorRT, right? And the mediator, or you can say the bridge format between the converter is your Onyx, right? And then after that, what we are going to do is you can perform inferencing, right? Because now the TensorRT model is ready to be deployed. It's fully optimized, right? Everything is good to go with this model, and it's very performant compared to the PyTorch model. So it's ready to be deployed, and now you can query. You can send queries to this model depending on where you have deployed this model, and different backends you can leverage to basically cater to the use case which this model was initially designed for. Next is Triton Inference Server. I only have one slide for Triton Inference Server. The reason being, I want you all folks to understand Triton Inference Server from code perspective, because there are a lot of features of Triton Inference Server, right? So it's more from a practical standpoint rather than a technical, rather than a theoretical topic, right? Triton Inference Server is nothing but it's a kind of, you can say, server where you can deploy your model, right, in one line. But point being, let's suppose you have a PyTorch model, right? You want to deploy it somewhere. Trivially, some of you might have used Flask, right? Some might have used serve your model in Torch serve. Some might leverage TensorFlow serve, right? But let's suppose if you have different models for TensorFlow, you can only use TensorFlow serve. You cannot deploy that model in Torch serve, or vice versa is true for the PyTorch model. But let's suppose I want in my pipeline there are multiple ensemble models, like right in sorry, some models are PyTorch models, some are TensorFlow models, and even some are TensorRT model, right? Because we are going to deploy ultimately TensorRT model, which is our most optimized model, or you can say model version which we have created, right? So in this Triton Inference Server, it supports multiple backends. In the sense, you can deploy Python model, you can deploy PyTorch model, you can deploy your TensorFlow model, TensorRT model. There is this forest inferencing library backend for machine learning models. You can leverage that. OpenVINO is also supported, right? Different backends they are supported. So you can create an ensemble, you can say customize ensemble pipeline, right? Based on your use case. If you want to have, let's suppose, end-to-end classification and segmentation problem, right? Then you can have your classification model in PyTorch, and you can have your segmentation model in TensorFlow, right? And ultimately you can deploy those directly in the Triton. Or even if the ideal scenario is once you have converted, once you have basically trained your PyTorch and TensorFlow models, what you do, the next step will be basically optimizing those models in TensorRT and then deploy as an ensemble pipeline in the Triton Inference Server. Right, and Triton Inference Server, it also supports both GPU and CPU. So if there is something you want to deploy on CPU, you can leverage Triton Inference Server for that, right? So once you have deployed, usually it supports two standard protocols, right? So those protocols are HTTP or gRPC to talk, or you can say to ensure the conversation or communication between the server client type of architecture, right? It supports dynamic batching. You can do the scheduling of the models, right? But ultimately it boils down to one point, that your model repository which you have on the right of your screen, it should follow a specific format, right? And that format is very essential, or it's most imperative thing which needs to be taken care of while you are deploying on Triton Inference Server, right? So what I mean by model repository is, let's suppose I have four models. By the way, this is my last slide, so we'll again be starting with the hands-on. So let's suppose we have the VIT torch model, right? Four class model. We have weights for that. What we'll do is we need to basically convert this model to ONNX first, right? And then to TensorRT FP32 and TensorRT FP16. And there is one more step in between before converting to Onyx. Because the function torch.export.onyx needs a torch script file. So you have to convert your PyTorch model to torch script model, right? So these are how many models? These are basically one model, two model, three, four, and five models are there, right? So you can, and the backend for these models need to be what in the inferencing server. For this, it will be a PyTorch backend, right? For this, it will be a TensorRT backend. So there are different multiple backends available, right? So what we are going to do in our next, you can say code walkthrough is, we are going to have a VIT torch model, and we are going to do this conversion, right? And we are going to deploy these four models. We are not going to deploy torch script model. We are going to deploy these four models in Triton, and then we are going to analyze the performance numbers. Again, by performance, now we are in the inferencing stage. So now we have to shift our focus from time to throughput and latency. Latency is also one of a time metric only. So we have throughput and latency. So this is what we are going to do. And the API for this, we are going to leverage for TensorRT. We are going to leverage what? We're going to leverage TRT exec, right? This is the command we are going to leverage. For performance, we are going to use something known as perf analyzer. It's a kind of stress testing tool. How much load or how much queries and batch size can your model handle? Perf analyzer. Okay, so this is the objective of the this hands-on which we are going to cover, right? For vision transformer. But before that, what I'm going to slightly change the workflow of these you know this upcoming demos. The point being, I want all of you to understand the TensorRT conversion, right? So we have different models. I have efficient net model. I have Monai based unit R model. So I am going to show you the TensorRT conversions for all the models to you, right? So you can familiarize with how the TensorRT conversion actually happens and how you can optimize it further, right? So let's get back to our demo part. Just a second. Any doubts till this point, anyone? Because next part of the session is going to very interesting. because deployment is what like most of you have to do if you want to make your research project or whatever application you're working in a more presentable scenario, right? And also it's a more if you're looking from an industry standpoint, this is the thing that can basically improve your model to a much more different extent. So any doubts, anyone till this point? I see there is no doubt. So let's jump right back in. So I have this model dot converter IPython notebook. Just a second. Can I get a confirmation if it is readable or it's visible? Anyone can confirm if they can read
Yes,
this?
Utkarsh, it is visible.
Okay, great. So let me rename this. So the first step is basically importing the again the libraries we want to do. Let me restart the kernel. So we have removed the libraries. I'm removing any Triton model repository which was already present, right? And then I'm going to make a Triton model repository folder. The reason being, you like if you can remember, I told that your Triton model repository should follow a pre-existing format which has already been set by the Triton team, and that format is inside the model repository which you have. You have the model, right? And inside this, you need to have a subfolder named as one, right? Inside this also we have one, inside this also we have one, inside this also we have one. That's why we are following this format, and in this folder you need to have, we'll add a configuration file for all the models, right? Because configuration file is something which will explain, or you can say tell the Triton inference server how to deploy that model, what is the kind of backend that needs to be leveraged, whether it needs to be deployed on a CPU or on GPU, how many model instances need to be deployed, how many GPUs need to be used. All of these things we mentioned in the configuration file, which we are going to design in some time. Next is what we have done is once we have created this repository, I am setting the path, right? So this is my input model. So my input model is what? It's my custom VIT model. So it's basically a PT model. Then I'm converting this model to a torch script format. Okay. Then what we are doing is we are again setting the path for Onyx. Dot plan files are also set here, and we are setting some additional parameters like number of classes and input shape. We are loading our model with the pre-trained weights, loading that weights to the model, right? And sending our model to the evaluation stage. Now is the time to basically change our model from your uh, PyTorch version to your Torch script version. In our case, mistakenly I have PT model already loaded here, right? But in your case, it will be your PTH model. Then you need to do this conversion. For that, what you need to do is you need to leverage torch.jit.trace, right? So it will accept two arguments as an input. One argument is your model, and the second argument is basically your example. Example is nothing, it's a kind of, you can say, garbage example which we have created, mapping to what input and input shape and batch size we want to have. And then we'll save this inside this jit underscore model path. Now the next thing is basically changing this torch script model to the Onyx model. For that, we are leveraging torch.onyx.export. Right. So this is again one of a very important command here. The parameters or syntax depends on kind of definition this command has. So we have torch.onyx.export. The input is the model, right? X is input model is basically your input model which we had, right? X refers to your again garbage input which we have set. Export params is basically your pre-trained model weights are loaded inside the model file, right? Offset version are for the version of the Onyx export which you are going to do. Input names is basically the name of the input and the output node which you will be setting or you can which you will be leveraging throughout the conversion which you want to do, right? And then these are two of the most important parameters, right? The first one is basically your input and the output, but it comes under dynamic axis. Now, what do I mean by dynamic axis? So basically, batch size or in a real-time scenario, let's suppose I want to deploy a VIT model in production, right? Or let's suppose again coming back to our search engine example, there will be multiple queries at a time, and the multiple which are I'm saying it will vary from time to time. Sometimes your batch size can be 64, or sometimes there will be 120 queries. There will be multiple concurrent requests, but your model should be capable of handling the maximum also and the minimum also, right? And for that you need to ensure that your batch size is dynamic, right? So that your length axis it becomes variable and your model is able to accept that as an input, right? The next thing like which we are waiting for quite some time is your tensor RT conversion, right? And for that what we want to have is basically we want to use our TIT exec command, right? And these are the flags which we need in that command. For example, first flag is your Onyx, right? So this is the path of the Onyx model. If you remember, and if I go back to the slides, we are at this stage where we have converted our model to Onyx and we want to convert our model to the TensorRT, right? So now what we are going to do is we are going to write this trt exec command, and these are the parameters or you can say arguments for that command or flags for that command. First is the path of the model. Explicit batch is basically again there are two options. One is implicit batch and the other is explicit batch. Explicit batch basically means that you can do dynamic batching with the model which you are creating. So you can send multiple batch size as a queries to the model which you are creating during the TensorRT conversion, right? And then next is the workspace size or workspace. It basically means the size of the workspace you want to allocate for TensorRT conversion. And you will see I've already ran this cell, and before it finishes, let me show you watch NVIDIA SMI. Because TensorRT is one thing which needs GPU for the conversion, right? And you can see GPU number one is being utilized for the TensorRT conversion, right? So just a second. So on GPU number zero, your TensorRT conversion is happening, right? And it is occupying your GPU for the conversion process which you are going. So you can see this trt exec command is occupying about 2 GB to do the conversion, right? The next thing is basically your OPT shape, max shape, and min shape, right? These are again very important for the model which you are going to convert, right? So OPT shape basically like full forms to optimal shape size which you want to have for the model. So my model is trained for 224 cross 224. So I'll rather keep that this as the input shape to the model which I want to draw inferences on, right? So here what we have done is optimal batch size we have kept as a 8, right? And these are the some of the numbers which can vary and which will vary depending on machine to machine, model to model kind of conversion you are doing, right? Maximum shapes we have kept as 128 as a batch size, and minimum we have kept as one batch size. If you want that your GPU should only handle multiple batch size as an input, then you can change the minimum shapes depending on your need. And then at last is your save engine flag. So what is the save engine? A save engine is basically where you are going to save your TensorRT model, which you are converting, right? So this save engine will have this path again inside this FP32. It will be going to get saved. right? Now my conversion is happening for vision transformer, and it will basically do your layer by layer conversion and all different type of optimizations which we discuss for TensorRT, right? After this is FP32 based conversion, right? Let's suppose I want to do FP16 TensorRT conversion. For that, there are nothing but two changes which you need to do in your command, right? So those changes are basically okay. Those changes are basically you need to change the model path. So here this was a model path for your simple model, right? And now your model path is changed to FP16 based TensorRT base where you want to save the FP16 model, right? And you will write an additional flag here hyphen hyphen fp16. So what this flag will do is it will indicate that, hey, now I want to convert my onyx model to your to my TensorRT fp16 model, and it will take much more time compared to the fp32 based models, because there are a lot more optimizations which need to be done when you need to convert from uh, your onyx to the fp16, right? So this is your entire TensorRT pipeline, right? Any doubts till this point? Anyone? No, no doubts. Okay, great. So now what we have done is our conversion is still going on. For FP32, it's complete. So let's scroll to the down. So you'll see this flag will come as a passed, right? If my conversion had failed, your flag or what the indicator would have been failed, and your conversion would have not worked. And there are different traces which trace runs which have happened here, right? And the throughput for that summary is your 116 zero point 0.9 inference queries per second, and there are different GPU parameters listed like host to device copy or GPU compute time, device to host latency, and different parameters, right? But again, the gist of this matter is that we have done or converted our TensorRT, or you can say PyTorch model to your TensorRT FP32 model, right? And our FP16 conversion is still going on. So meantime, the conversion is going on. What we'll do is we'll go back to our Triton model repository. Okay. So in Triton model repository, now we have four folders. First is VIT Onyx, VIT Torch, VIT TensorRT FP16, and FP32. The only reason I've created this four folder is I want to draw a comparison between, hey, how good my Torch model is and how good my FP16 model is. And what we'll do is we'll deploy this and we'll create a sort of application or app, right? So we'll create a sort of website here. So this kind of application we'll create, and we'll do the inferencing on this, right? And this we are going to do in Triton Inference Server. Okay, so be with me for some time now in the sense, so that you can get more clarity on the entire pipeline. And once you understand this VIT, trust me, all the other examples related to your unit-based vision transformer, medical image segmentation model, or you can say your arc face, which is the facial recognition model, all of those will become very easy to understand, right? And we'll end with the efficient net video conversion. So here, let's take this on a model by model basis. So let me open the configurations. So this is the model repository which we are going to deploy, Triton model repository. In this, we are going to deploy these four models. Let's start with the PyTorch. So inside this one will be what? Will be our PyTorch model. So model.pt file, right? Here, what we have to do is we have to create a configuration. So for configuration, the name needs to be same for everything. For example, here the name will be config.pbtx. So this is the proctor format which needs to follow for this configuration. So for this, what we'll do is we'll have this configuration inside this file, right? So what is this configuration? First, there are certain parameters which you have. So this is again Triton configuration. And now we are segueing from TensorRT to Triton because we want to deploy these four models, right? So here the name refers to the name of the this folder. For example, this folder has what name? VIT, or model name is what? VIT underscore PyTorch, right? And what type of model is this? This is the PyTorch model. So my, you can say my backend will be PyTorch underscore libtorch. Okay, so the backend will be PyTorch underscore libtorch. Then we have enabled dynamic batching, in the sense what will be the preferred batch size you want. If you want to keep it empty, you can. Your dynamic batching flag will be automatically enabled in the configuration for this. Maximum batch size, right? What is the maximum batch size your model can handle while inferencing? All these things like these are going to be very important if you are going to deploy any model in production, right? For different use cases you have for deployment, right? For real-time inferencing, it depends on the use case you are going to tackle. It can be your video analytics based use case, or it can be your speech use case. Everything boils out to this: how you have set the configuration, what is the maximum number of throughput, or what is the response you want to be. And you can set this batch size based on that, and also based on the GPU where ultimately you are running your model on, right? Next is your input and the output. So input to my model is what? It's a 224 cross 224 RGB image, right? And output is what? It's basically a four class. Like it will be a vector where there will be four. There will be basically four numbers, or vector whose length is four, right? And this four will be what? It will be the weightage to each class and telling us, hey, what is the class of this image, right? So this is your input. This is your output. Now what is next? Next is your instance group. Instance group has certain flags inside it. First is count. Count refers to basically number of model instances you want to deploy on a single GPU. What I mean by that is, let's suppose I want to deploy multiple PyTorch models on a single GPU, right? Because I want to increase my performance that much, right? So you can simply change this one to eight, right? And your eight models will be deployed on a single GPU, right? That's what a count is. Next is kind. Kind refers to the kind of backend you want to use. So this backend is this is basically a kind of platform backend, in the sense which type of model your file has, or you can say your model repo has. Here we have a PyTorch model, so we have specified the uh, backend based on that, right? Here is basically what type of, you can say, kind you want to use as a backend for processing your model, right? Whether you want to run it on a GPU, if you want to run it on a CPU, just add C to the G and you'll be able to run this from your GPU to the CPU. Again, if you want to deploy on multiple GPUs, you just need to change the number here, which GPU numbers you want to deploy on, right? And at last is your model.pt. This is your configuration file for your PyTorch model. Next is setting up the configuration for your Onyx model, right? Remember, we are deploying four models. We are going to compare all these four models, right? So we are going to have four configuration. Again, the format will remain the same. The name of the folder corresponding to the name of the model, we have named it here, for example, VIT underscore Onyx, right? And then what we have done after that is basically platform is Onyx runtime, because now we are deploying the Onyx model, right? So if I go inside this one, we have model.onyx. Inside this torch, you had model.pd. Now we have model.onyx, and I'm writing configuration for that. Everything else will remain the same. Your default model file name will change to model.onyx. and your platform will change to Onyx runtime underscore Onyx. And based on whatever name you have set for your input and output while doing the conversion, I've changed those names. So here those names are basically input and output. This is your Onyx configuration file. Next thing is basically your TensorRT FP32 configuration. Okay, so just a second. Let me copy that. So this is your TensorRT FP32 configuration. So I'll create again the replica of this configuration here inside the new repository, which I'm creating to deploy in Triton. So config.pbtxt, right? And here what we are doing, again, everything will remain the same. Now what we have done is we are going to shift our focus to TensorRT backend. So platform we are using TensorRT underscore plan, and the model we are changing it to model.plan. So if I go inside one, we have model.plan file, which is the file like pt file or .onyx file for the model, right? But this is a TensorRT optimized model. It can be .engine also. It depends how you have saved the model, right? So the only change I see is basically in the platform, right? And the model name which you have done, and corresponding to the model, what type of model you are giving to your basically uh, what type of model you are giving as an input during the configuration, which you are going to set on TensorRT while tracking deployment. The next and the last configuration file is your configuration file for FP16, right? FP16 we haven't, or you can say we need not change any backend. The reason being, because in FP32 your model was what? Your model was TensorRT, right? Now also our model is what? Our model is TensorRT model only. It's just that we are changing the model file. Now earlier it was FP32 model. Now it's a FP16 model, right? And that maximum batch size is 128. File will remain model.plan only. And let's see if our conversion is complete. Yes, it's complete. Let me rename and save it. Config.pvtxt. Yes. And now my Triton model repository is set and ready to be deployed. So what we have done till now is we are at this stage. We have prepared this model configuration, which is on the right. We just need to now deploy it, and let's see how our inferences and our performances. If we go back to our model converter, you can see the TensorRT FP16 conversion is also complete. And here for the random trace run, the queries per second were 247, because it's gradual, right? Now earlier we were doing on like 130 something was on FP32, right? And for FP16, now your model will be more compact and your results will be much more better compared to this. But these are on your trace runs which you are running by TensorRT and during your conversion, right? So everything is ready, right? Our repository is ready. Now just what we need to do is we need to deploy this in our Triton server. Any doubts till this point, anyone? uh, Folks feel free to ask the doubts, else like uh, you won't be able to understand upcoming sessions, or you can say topics which we are going to cover. Okay, there is no doubt. Cool. So what I'm going to do is I'm going to run now Triton server container, right? And inside that container, I'm going to deploy my uh, just let me stop all the containers which are running. Now, the next step is basically, let's go back to our notepad, right? We have these four models. We have the four configurations. Our Triton model repository is ready with four models, right? And corresponding configurations. Ultimately, let's suppose you are building a image classification pipeline in deployment. You won't need these four models, right? You only need the best model for your use case. The reason we are deploying four models is we want to compare how good these models are, or what is the performance difference or jump we get once we change from TensorRT from PyTorch to your TensorRT model. Right. So what we are going to do is we are going to run a container in which in this container we are going to serve the tensor art, the model repository on Triton, which we have created. So just give me a second. I'll deploy this on, let's say, GPU number 0. And this is the Docker run command which I'm going to use. Right. So Docker run hyphen IT for interactive hyphen net equal to host for enabling networking or opening all the ports which are there on the system visible to the container hyphen IPC, so that all the shared memory and the underlying workspace for the system is there on the Docker hyphen GPU's flag to allocate the GPU to the existing container which are going to run, not the existing, the container which are going to run. Then hyphen v is mounting, right? So this is the place where we need to make the changes, right? So hyphen v mount will be basically where the address of your model repository, right? Where actually your model repository is located. So let's see where our model repository is there. So inside this, there we have demos folder. Inside demos, we have IIT Bombay, right? And in IIT V folder, we have VIT. And inside the VIT, we want to deploy this folder, right? Triton model repository. So we'll mount only that folder to this. So Triton model repository, and we'll mount this to the models, and we'll be running the Triton server 22.04. 20 on 22.03 will throw error. The reason being, for conversion, I have used the TensorRT version, which is the more latest version compared to the version which is compatible with the 22.04 version of the Triton inference server. Now I'll run this container, and now I'm inside my container. Okay, and inside this container, if we go to cd models, or you can say if we can go to the models, you'll see all these four are there, right? And in these four, what is there, right? So inside this Onyx, you have again this config.pbtx, and one is there, right? So just a second, I'll clear all of this. So now the last, or you can say second last step, in fact, is to serve or deploy these models in Triton, right? For that, we are going to use Triton server command, and we'll set these flags. So I'll let it deploy, then I'll explain the flags. Okay. So in this, there are a few flags. First is the command you are running is you're running Triton server command, right? Because you are ultimately deploying your modeling Triton inference server. Model repository flag is, hey, where are your models actually record basically placed? Because as the flag name suggests, model repository means that uh, corresponding to on the right, I showed you this model repository, right? So that's what the model repository flag means, that hey, where is this model repository located in the Triton inference server container that you are using. Strict model configuration is, hey, whether you are giving the configurations or no, right? Sometimes, in some cases, some models run without configurations also. But ultimately, for creating a more practical scenario, you have to set this flag as true and have the configuration files. The config.pbtxt we have created, and log verbose is basically to print the entire in more detailed what is happening when the command is running. right? So if we go at the last of this, you will see if it is visible that gRPC and HTTP services are being basically this is the server you are using, right? What I mean by that is basically let's suppose I want to um, communicate with the server now, because that's going to be the next step. Till now what we have done is we have done this and we have deployed this on the server, right? Deployed 4 models on server. The next thing you are doing going to do is, let's suppose I have deployed some models for medical segmentation, but ultimately there needs to be some person using that, right? So that's the work, or to interact with the server you need to use a client, and sometimes your client or your server can be on the same system, sometimes it can be a local, right? So let's suppose big companies like Apple, Microsoft, Google, right? So these will, let's suppose they have deployed something for their public use case, right? Their data center, or you can say their server, will be somewhere else and their client will be somewhere else. This is for that what we need certain protocols to interact. gRPC and HTTP is what is compatible with Triton, right? If you want to leverage gRPC, it's 8000 into one port which is deployed, and this is by default it remains the same unless you have port forwarded while running the containers. Or for HTTP it is 8000, and you can basically uh, monitor what is happening in Triton using Prometheus or Grafana, and for that the port number is 8002, right? So our server is ready. Now let's go to the client. Any doubts, anyone, till this point? Because now we are at the last last stage of this deployment for VIT, right? So if anyone has any doubts, please ask so that we can have more clarity. Okay, great. So the next step is basically what you are going to do is you are going to have a client, or you can say application, which will basically interact with this server, and then at last we'll draw some inferences, right? So we have application.py and we have client.py. Let's run this first before basically seeing what's inside this. So I have already, if I do docker ps, I've already ran a Triton client server container. So my sorry, Triton client container, right? That is basically notated by SDK at the last, right? And this is my Triton server where I have done the deployment. So if I do, let's say, just a second, docker attach to go inside my client container, and now I'm inside my client container. Okay. Now what I want to do is I want to run this application. In this application, we'll come back to this what's exactly in this application. But first, let's go to the location where this application is actually located. Right? So I hope everything is visible to you. It's readable here. Now we are going to run this Python application. Okay, and for that, what we'll be leveraging is will be leveraging Streamlit for that purpose, and we'll be running a command which is Streamlit run. And let's run on server.port. Okay, 7001. My Streamlit application is running. Okay. Let's see on 7001. 7001. And here I have my final interface where we have deployed the application. We have yet to explore what is there inside this application.py, right? Because on the Triton server, what we did, we only deployed these four models, right? We have deployed these four models on server. We have yet to figure out what exactly we did on the client side that we got such an application. So if we click on browse files, I have some leaf. I hope you didn't forget what our initial model was. So we had a leaf classification model, the health of the leaf, right? So I'm uploading a healthy leaf and we are running our inference. Notice the four models. We have deployed four models here. VIT Torch, Onyx, FP32 and FP16. The only reason I'm again reiterating on this fact, the only reason we have deployed four models here is we want to show the comparison. In real world scenario, you only or you will have only one model of image classification corresponding to this task. You can have one for your shoe classification, one for your leaf classification, one something little to other kind of classification. But what I meant was in terms of the type, right? So let's run the inference on Torch and let's see the performance. So it took about 0.8983 seconds to infer on one image. Okay, let's note down these numbers. So torch number is basically your 0.898 seconds per inference. And someone asked me earlier that, hey, when you do this conversion, do you observe some kind of accuracy loss? Right, we'll also notice that there is no loss in the accuracy. The reason it is only showing 67% is because I've trained my model on less epochs. Right, you can obviously train your model for more epochs to get more accuracy. In our case, the focus is on inferencing and the focus is, do we get the loss in the accuracy or not? So it's a kind of relative numbers which we need to see. Next is we have done the VIT Onyx and we did the model conversion again, right? We ran the inference, sorry. So here from Torch to Onyx, so it was zero point 0.8 and 0.014, and the accuracy you'll notice is about 0.7, right? So accuracy is almost same. There is no loss, right? If we do FP32, it is 0.005, and performance is again same as the Onyx. So TensorRT FP32 accuracy is same as Onyx, sorry, not the performance, right? FP32 its number is 0.005, right? So you'll notice that there is some kind of improvement, right? And at last is FP16. If we run the inferences or FP16 again, there is some you can say discount in this case in the accuracy, but that's very insignificant in this case. You can always counterbalance that with the inferences here. And we have FP16 model and your inferences per second is 0.005. Yeah, some improvement from FP32, right? But at this point, a lot of doubts which I face is that, hey, these numbers are very insignificant, right? Why are you telling us to learn a separate SDK altogether, TensorRT? Like, because there is not much of impact which I'm seeing from Onyx, right? We'll see much more comparison now for these models, right? And we'll do the stress or the load test for this. Uh, so as a demo, let me give another image. This time it's a scab leaf, right? And I'll run the inferences. So now it is predicting that this category is your scab category. Okay. Now what I'm going to do is I'm going to stop this application which I'm running, and I'm going to do certain kind of stress test for this model which I've run, right? And for that, if you remember at the beginning of the session or when we were starting this, I talked about this perf analyzer, right? And for that, what we are going to do is we are going to run the perf analyzer to analyze these models performance in much more detail and with much more input, like more inputs with varying the batch size and all that. So this is the command for perf analyzer. So perf analyzer and then hyphen u localhost 8000. The reason being I'm using HTTP, right? If you want to use gRPC, just change this to 8001 and change this hyphen I flag to gRPC. Then measurement time interval is very small. I'll change to 5,000. Concurrency range is 1, and I'm running your VIT torch model. You'll notice this model name is same as this which I have deployed on Triton, right? So this should have stopped till now. Let's refresh. Yeah, it's down. And here you will see now it's running my VIT torch model. So on torch model, we got about 185 inferences per second with batch size of 1, and your latency was about 5407. Let's try with Onyx. So this 5407, or you can say 5K microseconds, it's the latency, right? And on the Onyx, you can see there is some improvement in the inferences per second, right? So from 185 inferences, or you can say the amount of images it was able to process, right? It improved from 185 to 223. Now the next is we are going to do inferences on your TensorRT FP32. So TRT. Let me check the name once. Okay, 363 queries per second, and let's run the FP16 also before noting the number for FP32 to save some time. Okay, so 363 here, and your 2750 inferences per second. You can see we started with 185 inferences per second, right? And the numbers they have improved to let me put pipe here, right? And we have improved it till now 363 inferences per second, and it's sending some requests in that time, right? And the last number which we have got is 456 inferences per second, right? For TensorRT FP16, this is the number which we got, and uh, this is the latency. So we started from 185 and we jumped till to 456, about 2.5x jump in the performance, right? But let's try now with multiple batch sizes. Okay, not multiple with batch size greater than one. Let's write it as torch here, right? And let's do with batch size of 64. Okay. So I'll only run the best and the worst one basically to see the comparison. We already have figured out that the trend is going that Torch is the worst here and TensorRT FP16 is the best model, right? So I have ran the TensorRT, the Torch model with batch size of 64. Let's try running with TensorRT FP16 now. And you can see in the server these are all the random queries which are being sent, right? I have not closed the container, and these are all the queries which are being sent in that time frame or time interval for that with the batch size of 64 for FP16, and we were able to achieve about 1088 inferences per second. uh, okay, for just a second, this 16. Yeah. So we achieved about 796 here, and with this, we got about 1088 inferences per second. So again, the spike from Tosh to TensorRT FP16 is evident. Now at last, if we see with multiple concurrent range, what we mean by that is you can have your concurrent range also multiple. So there can be multiple users which are sending their queries to the model, right? So let's have 126, 127, and this. How many parallel users or queries are we getting to this model? And then let's see watch NVIDIA SMI and let's see the utilization. So my tensor RT is being run on, okay, this proof analyzer. So it's running on GPU number 2. Let's see the utilization in the meantime. So So here now your utilization will be very spiked compared to the initial use case, because you can see here the concurrent requests were one. But so we got a throughput 1049, which we already got in the same ballpark here for TensorRT FP16. Also, I'm running the same model here. So it was TensorRT FP16 only, and now also I'm running TensorRT FP16 model, right? But we have sending concurrent requests to the model. So there will be much more load on the GPU. So only 50, 70% is there, which means I can increase this concurrent request to more than that to utilize it further, which indirectly means that you can increase the uh, you can say uh, we can increase the capacity, or you can say we can increase the amount of requests we want to infer, or we want the model to handle in that particular amount of time. So it increased to about 15 10.4 inferences per second with concurrent requests of 120. What would be the loss in the accuracy as we move from TOS to FP16? What we have observed, there is no loss, or it's almost same. The only difference comes is when you want to convert from FP to integer 8, right? Because it's a type of quantization, right? For that you have to write a separate calibration file, so that the accuracy loss which is coming, it's basically alleviated by referring to that calibration file. So this is the conversion we have done, and we have deployed our models and we have tested the performance, right? So let's come back to this. And here we have deployed 4 models: Torch, Onyx, TensorRT, FP32, and FP16. And you will notice, okay, what we'll do is we'll take a quick 10 minutes break. We'll reconvene at 5:20 before covering the client part and what's there in the client and how to do ensembling. Any doubts, please feel free to ask.